Okay, let's go for the next chapter. The next chapter is going to be chapter 18 is equation of state. In this case, we have gases and we're looking for the equation that um, represent the behavior of these gases. Let's do the same thing as we did for kinematics. Remember, we're dealing with motion, kinematics, and we want to describe that motion. How we described that motion? Well, once we know the position and the velocity of the particle at any time, taking acceleration to be constant. The same thing let's do right here. We have a sample of gas, right? And we have to describe the motion of this gas, the motion of the gas, correct? So we need an equation, and also we need to describe this motion. How we can describe it, or the state, we call this the state of the system. We describe it once we know the pressure, the volume, the temperature, and the number of moles. These are called the state variables, right? We have the state variables, state variables. We have pressure, right? Volume, temperature, and the number of moles to describe, let's say, the motion of the gas in a container. Okay, perfect. We are familiar with pressure, very well, volume, temperature, absolute temperature, and so on. Let's go to numbers of moles, right? The mole is a quantity. It's a unit used in chemistry, right? And 1 mole, right? And 1 mole is equals to 6.022 times 10 to the 23 molecules or atoms, right? This is 1 mole. It's like when you have 1 dozen. A dozen has 12 let's say objects, for example. This one, numbers of moles, 1 mole has this number of molecules, correct? Also, the numbers of moles is equals to numbers of particles divided by the Avogadro number, right? Avogadro's number is also defined in the same way as I relate actually to, from this equation, to numbers of moles, correct? Is equals to the same 6.022 times 10 to the 23, correct, molecules per mole, correct? That's gonna be the Avogadro's number. So and this is also equals to, if we multiply by the mass, right, of the gas, correct? We create now that 1 mole, numbers of mole, is equals to the mass of the substance divided by the molar mass. M, this big M is called the molar, right, mass, correct? The molar mass is just the molar weight expressed of an element, right, expressed in grams. For example, the molar mass of oxygen, the molecule of oxygen is 2 times 16. Remember, the weight, the mass weight for oxygen is 16. So at the end, what do we have? Because is this a diatomic molecule? 16 times 2 equals to 32, right, grams per mole. That should be the molar mass, for example, for the the molecule of oxygen, correct, and so on. Perfect. Now let's take this information to find the equation for an ideal gas. Okay, let's do it. So imagine that we have a sample of gas, a container. We have a container right here with some pressure. What happens when we increase the pressure? Let's increase the pressure right here, right? More mass. What happened then? Well, if we increase the pressure, in this case is a constant temperature, correct? Constant temperature. Let's see what happens to to the pressure and the volume. At the beginning, it is initially, we call this a state, right? State. So we have the first state and the second state. What happens in the first state? Well, we have this condition, pressure 1, V1. In the second state, we have pressure 2 and V2. Correct? Of course, if we increase the pressure, the volume decreases. Correct? So what do we have then? We have the pressure is inversely proportional to the volume at constant temperature. Okay, now let's eliminate this symbol, and what do we have? Pressure is equals to a constant of proportionality, right, divided by the volume. Or we can say that pressure times volume is equals to a constant. Okay, this product is the same right here in this state, and in the other state, right, as long as T is constant. Also, in general, we have to use numbers of moles is also constant. Okay, for all of these cases. Perfect. Means that for condition 1 is equal to the same, right, product to condition 2. Okay, and this is called the Boyle's law. Boyle's law. Perfect. It's a very important law. P1 V1 is equals to P2 V2. Okay, the product actually of these two quantities give us the units of energy. So this quantity is very, very important in physics. Okay, great. Now let's go to the other case. Remember, we are working with the variables, the state variables, correct? Which are pressure, volume, temperature, right, and numbers of moles. Okay, let's go to the next one. Let's take pressure constant. Okay, constant. Perfect. And let's work only with all the time, right? And I'm gonna be constant numbers of moles. Now let's work with volume and temperature. Perfect. Imagine this is again case 1. We have some pressure, correct? Then we have some temperature. Let's say volume 1 and temperature 1. Later, let's increase the temperature, correct? Imagine it's the same mass, correct? It's the same pressure. Now let's increase the temperature. What happens with the volume? Well, the volume increases, correct? Now we have another state, correct, represented by these new quantities. Perfect. Now, how these two quantities then are related? Well, in this way. Volume is proportional to the temperature. If we increase the temperature, we increase the volume at constant pressure. The same thing as before. Let's eliminate this symbol, and what do we have? Volume is equals to K times T. Correct? Now let's solve for K. K is equals to volume divided by the temperature. The same thing as before, correct? As in Boyle's law, we have that V1 over T1 is equals to what? V2 over T2. This is a new law. This is called the Charles law. Correct? Charles law. Okay, where? Okay, right here. Charles, right, law. Perfect. So do we have V1 over T1 is equals to V2 over T2. Now let's go to the case when volume is constant. Perfect. Let's do it. When volume is constant, now it's gonna be this volume right here and this volume right here, correct? At the beginning, well, in this case again, V equals to constant. Perfect. So which quantities are changing? Pressure and temperature. Okay. Again, N is constant too. So what do we have? Pressure and temperature. Correct, case 1 and case 1. Now let's put some heat right here to increase the temperature. So we have a new state, correct? And what should be that one? P2, right, T2, the new quantities. Because there is constant. Perfect. Now the same thing as before, how these two quantities are related? Well, pressure is proportional to the temperature. You increase the temperature of the object, we increase the pressure of the system, we increase the pressure too. Okay, perfect. The same thing before. Pressure is equals to a constant times the temperature, correct? Now let's solve for K. So K is equals to P over T. That happens for this state, also happens for this state. It means what? It means that P1 over T1 must be equals to P2 over T2. Correct? And this is another law. This is called the Gauss-Lussac's law. Okay, gonna be the Gauss-Lussac's, right? Lussac's, right, law. Perfect. So we have another law right here. P1 over T1 is equals to P2 over what? T2. Correct? Now, what happens when we involve numbers of moles? Actually, let's see what happens when we involve the numbers of particles. Let's do it. So when we involve the numbers of particles and we relate that to pressure, we can find that pressure is proportional to the numbers of particles. We found before also that pressure is inversely proportional to the volume, right? And we found also that pressure is proportional to the temperature. Okay, let's see what happens when we combine all of these quantities. Let's do it. Great. Remember, these are factors. These are factors that are related to these factors of pressure. Okay, great. And then what do we have? Pressure is proportional to numbers of moles, right, times temperature divided by the volume. So, numbers of particles. Numbers of moles, remember, is this little n, big N, numbers of particles. Numbers of particles, correct, times the temperature divided by the volume. Perfect. Let's eliminate this symbol. So pressure now is equals, right, to Kb. This is a special constant. This is called the Boltzmann constant, right, times N times T divided by V. Correct. And we got to, we are rearrange this equation in this way. PV is equals to Kb and T. The value for K, right, the Boltzmann constant Kb is equals to 1.38 times 10 to the negative, right, 23 joules per Kelvin. Joules per Kelvin. That's gonna be the magnitude for Boltzmann's constant. Perfect. Now we are right here. Correct. Now let's see what happens when we involve the number of moles. Let's do it. The number of moles. We are right here. PV, right, is equals to Kb, right, and times the temperature. Correct. I remember numbers of moles equals to numbers of particles divided by the Avogadro's number. Correct. From here, n numbers of particles equals to numbers of moles, right, and the Avogadro's number. Correct. Now let's substitute this value right here, and what do we have? We have that PV is equals to n, right, Avogadro's number Kb times the temperature. But look, remember it's a constant. Avogadro's number is a constant, and this is another constant. So when we multiply these two constants, we create a new one, and that constant is called R, right? The gas constant or the universal gas constant, right? So PV is equals to nRT, and this is the ideal gas law. Okay, ideal, right, gas law. Right, or the equation of state for an ideal gas. Equation of state. Equation, right, of state, correct, for an ideal gas. Great. So we have a very important equation, maybe because this equation describes the state, right, of a gas. Depends on what? Depends on the pressure, depends on the volume, depends on the numbers of moles, and depends on the temperature. Correct? Perfect. Equals to nRT. In this case, we know that pressure is absolute pressure, correct? V is the volume. V is the volume, correct? N is the numbers of moles. R is the gas constant or universal gas constant. The value for this constant is, it has different values, but let's use this one, is right equals to 8.314, correct, joules per mole per Kelvin. Okay, and T is absolute temperature. Absolute temperature. Okay, these are the variables of state, correct? That's describe each state of a gas, ideal gas. We have another equation of state, right? This is called the van der Waals equation. It says that pressure plus A times N square, correct, divided by V square plus times volume and B is equals to nRT. Okay, this is for real gases. Real gases. This is for ideal gases. Okay, usually at this level we use mainly analysis for the ideal gases. This is for real gases. Again, we have PV right here, PV, nRT, but we have to take into account the interaction of the molecules, the volume of the molecules, and so on. Okay, perfect. Now, let's see what happens when we want to plot this law right here that we have. Okay, let's do it. For example, when we are dealing with pressure and volume, right? Pressure and volume, correct? From this equation, for the general one, what do we have? P pressure is equals to what? nRT over V. Remember, this is the case when the temperature is constant. This is the Boyle's law. Okay, great. Means it's constant. So what do we have? Well, we create these hyperbolas, right? Like that. Correct. Actually, this parabolas, right? Parabolas. Okay, perfect. And when we increase the temperature, okay, we increase the distance, or we increase in this case the volume, right? So what do we have then? We call this T1, T2, right? T3. In this case, T1 is less than T2 is less than T3. Perfect. How we can find that? Well, we take, for example, this line. This is V, right? When V is constant for this line, correct? What happens to the temperature? Correct? It's found that if volume is constant, if we increase the temperature, we increase the pressure. Remember, that is Gay-Lussac's law. Okay, that's why actually going to behave. The temperature behaves in that way. This has a special name. These are called isotherms. Right? These lines, these curves are called isotherms. Special name. Perfect. Now let's see what happens for the other law. Right? This law right here. What do we have? We have let's say volume and temperature, and then this represents the pressure, right? The pressure. Use again the ideal gas law. What do we have for the ideal gas law? PV is equals to, right? Now let's solve for what? Let's solve for V. So the same thing as before. So V is equals to N, right? R over P, correct? Times the temperature. Now these represent the slope. Okay, it's like a linear equation, and this is the slope. Correct. Now, what happens if we increase the pressure? Because these represent the pressure, right? What happens if we increase the pressure? What happens what should be the slope? What happens to the slope? Increases or decreases? Right? Where it increases pressure, right? This is constant, the slope decreases. Correct? So again, let's take this idea, and what do we have? This is pressure 1, pressure 2, let's say pressure 3. The same thing as before, right? What do we have? That pressure 1 is less than pressure 2 is less than pressure 3. Correct? The slope decreases if we increase the pressure. Correct? It looks like that. I think it looks like that. Correct? Or increases. The slope increases. If we increase the pressure in this case, or should be the opposite. Okay, let's double check this one. Let's take one constant temperature. The temperature is constant. Let's see what happens when we increase the volume. Right, what happens to the pressure? Or when we increase the pressure, what happens to the volume? Well, in that case, happens the opposite, right? It's found that if we increase the pressure, the volume decreases. So means actually that this is gonna be the opposite, correct? It's gonna be like this, correct? It's gonna be, no, it was correct, it was correct, it was correct. It was correct, right? It was correct. Because again, one more time, if we increase the pressure, right? If we increase the pressure, the volume decreases, correct? So if we increase the pressure, the volume is decreasing in this direction. So it's gonna be then, it was correct before. Okay, so this is P1 is less than P2 is less than P3. Correct? It goes like that. Perfect. Now let's go for the last one. Here we. The last law. Okay. The same thing. We have this one. This time pressure, correct, and temperature. What do we have now? This is volume. Okay, because this represents again a linear equation. We have pressure is equals to what? And R over V is now the slope, right, times the temperature. Correct? And now the same thing as before. In this case we have V1, right, V2 and V3 for example, and it's found that I behave the same thing as for this case, correct? The same situation. Okay, so what do we have? We have that V1, V2, correct, and V3 are coming in this way. Perfect. So that should be the graph, right, for these three laws. Perfect. Now let's go to the case when we want to relate the motion of the particles to these state variables. For example, to pressure. Let's do it. Let's do it. Let's see how the macroscopic system is related to the microscopic system. Let's do it. Perfect. Let's do it. Let's do it. So let's find pressure, right? Pressure of the system, pressure of the gas, equals to what? We define pressure as force divided by the area, correct? Perfect. Now imagine that we have a sample of gas, right, in this box, right? We have a box right here, correct? Imagine this is the box right here. And this is L, these are the dimensions, okay? This is Z, correct? This is what? X, and this is, let's say, Y, correct? Y. Perfect. Imagine that we have this, only this wash right here, and we have a particle moving, right? This mass with this initial velocity hitting this wall. Now, later, because we are dealing with collisions, we have the elastic collision, correct? And we have the final velocity. Perfect. But also force, remember, is related to momentum, change in momentum, right? Force equals to change in momentum, correct, respect to time. Remember, when we're dealing with collisions, we have two types of collisions, especially, right? We have elastic and inelastic collisions. For this example, right, we are taking the collision of the molecules of the gas, right, and the walls, right, to be completely elastic. So it means energy is conserved, right? If energy is conserved, remember we mentioned that PV is equals to nRT, so PV has units of energy. Means what? That this is energy, kinetic energy must be proportional to the temperature. Let's find that condition, okay? That the kinetic energy is proportional to the temperature, to the absolute temperature. That's the goal for this analysis. Okay, let's do it. Let's do it. So what do we have? Let's find momentum. Momentum is equals to, actually change the momentum, correct? It's final minus initial, correct? Perfect, but what is final? Final is remember the magnitude is the same, right? We change only direction when we have elastic collisions, correct? So it's gonna be final, right, minus initial. Is equals to, because the magnitude is the same, right? And this becomes positive, it's gonna be twice, of course, times mass, right? Times mass. Okay, it's gonna be mass times, or actually two times mass times v, correct? The speed, or the magnitude of velocity. Perfect. Now let's go and, well, from here, look, we can say that volume is equals to L cubed, or we can say that area is equals to L squared. Perfect. Okay, great. Now let's substitute this value, correct, right here. And what do we have? We have the force is equals to 2 times mass times speed. Okay, perfect. Divided by delta t. But delta t, right, is a time. If we're taking only, let's say, imagine that right here we are only in the x direction. Okay, x direction. Okay, let's take only in the x direction. Perfect. So imagine that we are in the x direction only, right? And we're looking for the collisions on this wall for that particle. So what is the time? So the particle is coming, right? Collide, goes back, and go back again, collide again. So in this case, we know that speed is equals to distance, right, divided by the time, correct, or delta t. Perfect. What should be delta t? Delta t is equals to distance divided by, right, speed. But what is the distance? The distance is, okay, going from here to here and go back, right? It's twice. This is L. It's gonna be 2L, correct? So it's equals to 2L divided by V. When we substitute this value, this is changing time. Okay, when we substitute this value right here, what do we have? Well, this becomes equals to speed in x direction divided by 2L over V, correct? And this is equals to mv, right, squared divided by L. Okay, so that's the force done by each particle on the wall. Okay, perfect. Now we're dealing with velocities, right, or speed, but the speed of the particles, even though they have the same mass, they're not the same. They have different speed. To simplify this analysis, let's look for the average. Oh, by the way, this is only for one particle. Let's see what happens if we have n particles. And let's find the net force. Okay, what should be the net force? The net force is equals to the sum, right, of right, the forces, and this is for let's say one particle. You might say for one particle, this is one particle, correct? The same thing happens right here. It's gonna be for n particles. It's gonna be the net force is gonna be the total the mass of each particle, right, times, right, the sum of these particles the speed of the particle square, correct, divided by L. This is for n particles. Okay, because this speed are different, they're not the same. Let's find the average. Okay, let's find the average for each particle. The average, for example, for average square, correct, is gonna be equals to, right, the sum of this, all of these speeds, right, the square or velocity squares divided by n, correct, the number of particles. Perfect. And now from here we can see that we can solve for this quantity, right? From here the sum, right, of all these particles, the square is equals to n, correct, times the average of this square, correct, of the same quantity square. Perfect. The average. Great. Now we substitute this value, right? This value right here. And then what do we have? Well, you can see this equals to m over L times what? Times n, correct? Times this average square. Correct? Average velocity square. Perfect. Now we substitute this value. Let's go back and substitute that value right here. Okay, let's do it. Let's do it. So let's go to pressure again. Pressure is equals to m n, okay, times the average of the square, correct, of this quantity speed, divided by L, correct, divided by L times the area. But area is equals to what? And L area is L square. So when we multiply these two, what do we have? L cubed, right? But L cubed equals to volume, correct? So this equals to what? From here we have that PV is equals to n numbers of for each particle, correct? V, the average of the speed, correct, times the mass. Perfect. Now, because we have mass in v squared, this quantity, this product is familiar to us, right? This is related to kinetic energy, translational kinetic energy. Remember, the translational kinetic energy is equals to mv squared over 2, correct, over 2. So look, we have these two quantities that are in the definition for kinetic energy, so we can rearrange it to create translational kinetic energy in that equation. Okay, let's do it. But look, this is in the x direction. Let's see what happens to find the net velocity. Okay, remember when we're dealing in 3D, we found that v is equals to, v squared is equals to v x squared plus v y squared plus v z squared, correct? Because we're dealing with average right here, we can do the same thing for these averages. So we have that the average, right, the square, v squared is equals to this vx, right, average square, right, average plus this vy square, correct, the average, and the average, right, of vz square, correct. But these velocities have the same, the particle has the same probability, or the velocity is the same probability in x and y directions, correct. So we can say that these are the same probability. So this is equals to we can approach this to three times, because it's are the same, 3 times the average velocity, right, in the x direction. In the x direction. Now from here, right, we can solve for this quantity which appears in this equation, and we can say that this average, right, is equals to 1/3, correct, this final average velocity, correct? When we substitute this value right here, what do we have? Well, we have that PV, right, pressure times volume, is equals to N mass, correct, V final, right, the square, right, taking the average, correct, divided by 3. Perfect. But we already know from the ideal gas law, right, this product, right, this product is equals to nRT. Let's compare this to see what do we have. Actually, from here, look, if we multiply and divide by 2, right, multiply and divide by 2, correct, what do we have? So this is equals to multiply and divide by 2, we have 2n, right, over 3, correct, times times what? Times mass of V average square, correct, divided by 2. But what is this? This is the translational kinetic energy, correct? So it's equal to 2/3 n times the translational kinetic energy. So PV again is equals to this quantity. Now let's relate or compare, right, these two formulas, and what do we have? So we have that nRT, right, is numbers of moles times the gas constant times the absolute temperature is equals to 2/3 and translational kinetic energy. Correct? Perfect. And from here, we can look before that, because we wouldn't want n. We have an let's substitute this value to eliminate n, right? Yeah, it's okay. So we can use Boltzmann constant n, right, times temperature. In this case, right, we are canceling the numbers of particles, atoms, or molecules, correct? So from here we can find that the Boltzmann constant times the absolute temperature is equals to 2/3, right, the translational kinetic energy. So this equation is very important because we can see that the kinetic energy, translational kinetic energy of the molecules in a gas, correct, is proportional to the absolute temperature. And that's one of the definitions for the temperature, right? At the beginning, the previous chapter, we tried to define temperature. It was not easy to define it, but we can define it in this way, right? The absolute temperature is proportional to the average. This is the average kinetic energy, right? It's coming from this average of the molecules in a gas, in a sample, right? Perfect. So this equation is very, very important. So we have Boltzmann's constant times absolute temperature equals to 2/3 times the average translational kinetic energy. Perfect. Also, we can solve for this translational kinetic energy. Translational kinetic energy equals to, according to this, 3/2, correct, kV over times temperature. This is for one particle. Imagine that we have n particles. So for n particles, what do we have? The translational kinetic energy equals to 3/2 n kV, right, times the temperature, absolute temperature, correct? But n, one more time, remember, use numbers of moles. N is equals to numbers of particles divided by the Avogadro's number from here, correct? Numbers of particles equals to numbers of moles, right, times Avogadro's number. When we substitute this value over here, what do we have? Well, translational kinetic energy is equals to 3/2 times n, Avogadro's number, times Boltzmann's constant times the temperature. But what is this? One more time. This is R, right? The gas constant or universal gas constant. And then what do we have at the end? We have that this translational energy is equals to 3/2, right? N or T. Again, and we relate the motion of the particles, the average energy of the particles in a gas, to the absolute temperature, right? The gas. Okay, and with this, we stop this introduction for chapter 18, equation of state, and we finish the chapter in part 2 of this chapter. Okay, the next video. Okay, great. See you in the next video.